Let's take a look at an example. And the example we're going to use is that of the Bohr model. So if you're unfamiliar with the Bohr model, it just pretty much says it's a model of the atom. It says that we have a nucleus, and that nucleus is surrounded by energy levels. And each of these energy levels, for instance, the lowest energy level, n equal 1, is just a small little orbit that the electron can go around in it. And the energy for that energy level is given by this famous equation normally. It's negative 13.6 electron volts divided by n squared. And that's the energy that that electron has if it's circling around in that orbit. And this is where we actually get into a concept of quantum mechanics, where these energies are actually quantized. So an electron can be here, it can be here, but it can't be in the middle region inside. So as we get to larger n's, we can look and see what happens to the energy levels for these. So just a very simple equation. It's the minus 13.6 electron volts. And electron volts is another energy unit. If you're more familiar with the MKS system, it's 2.18 times 10 to the minus 18 joules. So we can ask a question based off of this. And the questions we're going to ask is what happens when something transfers between one or two energies. So let's say the electron starts in some energy and goes down. Well, this means that when the electron goes from one state to another, it's either going to gain or lose some energy. So for the Balmer series, this is just the designation we call where we end up in n equal 2. So we're going to start at some transition and go to n equal 2. So if we go 3, 4, 5, 6, 7, so on and so forth, as long as we end in n equal 2, we call that the Balmer series. Similarly, the Lyman series is when we end in n equal 1, when we end in the ground state. And hopefully you guys have seen this before in a chemistry class, what the energy levels are. But we're going to actually look at a little bit more of the physics behind it. So if we look at these, there's all these different energy states, and we can go up as high as n equal 30 for these different energy levels. It's kind of remarkable. But each of these levels is characterized by this equation. This equation is just for the hydrogen atom. There's a modification you can place for other atoms, but we normally see this hydrogen atom. So let's ask the question. What is the wavelength of the emitted photon? Or absorbed photon? We know that the energy required to move between, say, two states, n equal 4 and n equal 1, in a hydrogen atom, it's going to require some energy changes. And one of the things that we can use a photon to either absorb or remove this energy or to put energy into the system. So we ask, what's that energy of that photon? So again, we have our energy levels, n equal 1 through n equal a lot. And we're going to ask what happens when we go from n equal 4 down to n equal 1. And this is, if we remember from the previous slide, in the Lyman series. So if we start going through this, we calculate minus 2.18 times 10 to the minus 18 over 1 squared. We're doing our final minus our initial. So we subtract our final state, our initial state. Initial state is minus 2.18 times 10 to the minus 18 over 4 squared. Started in 4, ended in 1. So if we subtract off these energies, we get minus 2.04 times 10 to the minus 18 joules. And then this is where the interesting, well, some more of the interesting physics comes in. We know that the energy for a photon, so this is the energy that's released from the system, it gets transferred into a photon here. That energy is given by hc over lambda. So we change around our equation, we get lambda is equal to hc over E. And if we calculate this out, substituting in this guy here, plus h plus c, c is the speed of light, h is Planck's constant in whatever units you're using, and we find that it's 97.2 nanometers. So since this photon is emitted, this energy is, we go to a lower energy, that means that the photon has to gain some energy, so that means we release this energy in the form of a photon, so it's emitted or produced. And since its wavelength is 97.2 nanometers, this is not in the visible range. This, however, is in the UV range, and UV is not visible light, but this is characteristic of the Lineman series, as they all tend to be in the UV range. So just a simple calculation showing that we can use the energy of a photon to figure out its wavelength. And knowing that if we have a transition between two different energy states, that the energy is neither created nor destroyed. This is just a conservation of energy problem with a new type of energy, and that energy is the energy of a photon.